Can you hear what I'm saying? Hello?
Yes, yes, we can hear you.
We can. So maybe we can start now. Professor Lopes, would you please share on the presentation?
Let's see if I can. Where is it now? I've opened. Okay, right here. So can you see the
Yes.
slide?
Yes, we can see. Thank you. Thank you. Okay, so shall we then begin?
Sure.
Okay. So the talk is of 45 minutes. So since we're starting slightly late, we'll also finish after 45 minutes. Okay, so welcome to this session of plenary talk. It is my honor and pleasure to introduce Professor Hedibert Lopes. And he's going to give a talk today on decoupling shrinkage and selection in Gaussian linear factor analysis. And he happens to be an expert in this area. And he is a professor of statistics and econometrics, and also head of the Center for Statistics, Data Sciences and Decision in INSPAR, the Institute of Education and Research in Sao Paulo. He did his PhD from Duke University, and then he has been in various places, including he was in Rio for some time, then he was in the University of Chicago, and now he is in Sao Paulo. And he has served in many journal editorial boards, various scientific committees, and he has won many awards and fellowships. His CV is really long. It's very difficult to introduce him, honestly. And also he has, supervised many students, both master's students and PhD students. So he has a huge contribution in academia. So it's really my pleasure and honor to introduce him. So without further ado, I would like to give the floor to him, and it's his. He's going to give the talk on Gaussian mixture models, essentially. Okay, thank you. You can start.
Okay. First, I want to thank you for the nice introduction. And also, it's unfortunate we cannot have this meeting, in person. I was in India 16 years ago for a Bayesian meeting in Varanasi University, and was impressed by the diversity and culture of the country. So, in any case, I'm also proud to be representing Brazil in this meeting, and I hope you guys can take some of this of what I'm gonna say, and then hopefully read the paper and get into this decoupling, shrinkage, and selection. This year, I'm on a kind of sabbatical, extended sabbatical here at Arizona. So it's in fact 6:30 a.m. here in the U.S. The reason I asked to give the talk at 10:30 or so, or in late morning, was so I could, wake up at 6 a.m. to give this talk. And these days, with everything done in via Zoom, we invite people from other places. Like the last week, we had a seminar speaker from Japan, so he gave a talk at 10 p.m. In Tokyo, and that was 10 a.m. in São Paulo, and then 6 a.m. here in Arizona, where I'm staying, for a year. So this is let me get to give you like an overall view of this research. You can find, as Professor Roy just mentioned, you can find this paper and the slides on my webpage, which is just my first name.org. You can go to the papers there, and then you'll find a draft, which is a second round. We just got back from Bayesian Analysis Journal, like a revised resubmit. So it'll be like a third round, and hopefully this time the paper will be published. But the current version is pretty decent already. It's on the web. It's on archive, so it's publicly available. And this was part of Henrique Bofarini Henrique's research on for his PhD thesis under my supervision. The other two co-authors are professors at the University of Texas in Austin, where he spent part of his PhD, like actually the last bit of his PhD. He defended in late October, and now he started as a postdoc there. So he's gonna continue his training there, finishing a second paper. The second part of the talk here, which is the second part of the title of the talk, when we talk about Gaussian mixtures, we will probably not have time to describe here, but that's a second paper we are working on. And for those of you who are in statistics, and know a little bit about the Brazilian history of statistics, Henrique is actually the son of Heleno Bolfarini, a very famous Brazilian statistician that got the Mahalanobis Award I think this year, and who has passed away like a couple of months ago, like 4 or 5 months ago, after 10 years battling, Parkinson's disease. And so, but he left like a big legacy in Brazil and in many other areas. So without more like historical events here, let me go and give you like an idea of what this DSS framework is. Okay, let me see if I can move around. So one of the things that people are spending a lot of time these days is on variable selection through sparsity. So it became like a very famous, very popular, topic when you have like large regressions with large number of regressors, and you want to do variable selection. Actually, this is a problem that has been in statistics for the last, 50 years, 60 years. So it started back then when we had the stepwise, forward, backward, stepwise selection as a very clever strategy in the 60s, 70s, and 80s. Then from a Bayesian point of view, we would include priors that were a mixture of point mass at 0 plus a continuous distribution for each one of those coefficients in a regression, and do 2 to the power of p possible visits of the modes of the posterior distribution. And of course, when p, the number of variables, increase, we have like an infinite number of potential modes. So that was really painful. But in the late 80s, early 90s, there was this idea of still using the standard ordinary least square scheme, or maximum likelihood schemes, Gaussian maximum likelihood optimization, but with a penalty. And that penalty, depending on how you pick that penalty, you can force coefficients to not only shrink towards 0, but also collapse as 0 in the optimization. And that's the idea of the lasso and all the lasso family. So instead of like when you maximize a function or minimize a function, instead of finding something near the maximum, you actually force some of these components to collapse at 0. So in that sense, you're doing what we always wanted to do, which is zeroing out some of these coefficients. So then there was like a huge amount of research on that from a non-Bayesian point of view, using LARS, lasso, group lasso, and many other techniques. And that is spread through many other areas, not only regression. From a Bayesian point of view, we also did, spend more time, because Bayesians already talk about priors all the time. So we say, okay, so what these guys are doing, the non-Bayesians are doing, is, cleverly picking the priors that we call priors, but they're calling penalization. But then there is like a large literature on, sparsity inducing priors. So then you see the Bayesian lasso, which is a natural extension of the lasso. Afterwards, there were priors like the spike and slab lasso, the horseshoe prior, and the normal gamma prior from Europe, and then the triple gamma prior of Fruition. So and that was the focus, trying to get the penalization or the prior to, we put all the effort into the prior to make the selection. So the idea of the DSS, that is this decoupling, shrinkage, and selection, was basically saying, well, you know, if we go back to what Bayesians would do on a regular basis, you would set your prior according to your expertise in a particular context, problem, and then combine that with the data that you have. You would have posterior distributions, predictive distributions, and after that, you would combine, you know, the most relevant and most recent summarization of the posterior distributions you have at hand with a utility function or loss function, and then that will govern how you make your decisions. So from a Bayesian point of view, there is a tripod. So you have prior, a model, and a utility function. So the utility function says, well, what do you do once you get updated information about this particular event? What kind of decisions you have? What are the actions and the consequences of those actions? So what the DSS is basically doing is going back to the origins of Bayesian statistics and say, well, let's liberate, let's free the prior from this burden of being sparse from the beginning because we don't know what's going on. And then let's put that burden into the utility function. Let's move that to, you know, the third step of the tripod of Bayesian thinking. Okay, so this is what I was trying to do here. When we say, oops, sometimes the mouse takes over. Let me go back here. When we have this decision theoretical approach, we have a prior, the model, the utility, and the action for us will be this gamma, like very generic right now. So there is a gamma set of you know, variables that we want to select, thinking about the regression setup for now. So do you see the little hand when I move here in the screen? Or
Yes, we can see that. Yes.
yeah, because I don't have a other way to mark where I'm at in the slide. So I'm going to use that little hand as a pointer. So the optimal action is that one that maximizes the utility. And for us, the utility here will be based on the posterior predictive. So if you're familiar with Bayesian statistics, what we are actually doing here is taking the expectation of future events, because we don't know them, so we take the expectation, conditioning on existing data. So that utility function is going to be maximized up to a cost that involves like the complexity of the model, and that's where, you know, all the idea of the lasso and the other penalties will come in. So it's something that is done a posteriori, and then you penalize. So I mean, I could stop my talk right here and say, well, this is what we're going to do for factor models. We're going to run our factor models from our favorite package from a Bayesian point of view, even if it's not Bayesian, but let's assume we're all Bayesian here. We feed a factor model, then you say, okay, so now that I feed a, you know, a saturated, complete factor model with way more factors than I think is necessary, now I want to penalize the number of factors and also the structure of the factor loading matrix a posteriori with a particular utility function. You know, so this paper that Richard and Carlos wrote back in 2015, I think, or maybe 2016, I'm not sure. It's a JASA paper where they introduced this idea that you take your utility function, and we as statisticians, we like loss functions more than utility functions. Economists like to call utility because it's a positive thing. For statisticians, we are pessimists. We like to talk about loss functions. So when you take a loss function and then you penalize, now your question is, what are the values for gamma here that will, you know, minimize instead of maximize my loss? Okay. So it's a three-step procedure that uses a very generic loss function. Okay. So the second step was I need to integrate over the future because I don't know. I have only the uncertainty about the future given the past. Imagine like if you are in economics or these days we're talking about COVID and things like that. You want to forecast next week's, causalities or infections, whatever, condition on all the data up to now. But we don't know what's going to happen next week. We only have this uncertainty through the probability distribution. So your actions, should you shut down the airports, or should you give more masks, or should you make more tests, whatever they are, they're going to be maximized or minimized over this predictive distribution. So what you see is like, what is my expected loss when I make a particular decision? And so we use the standard paradigm of minimizing expected losses. And as I say here, this predictive distribution or posterior predictive distribution is the integration of the likelihood function, which is your model, whatever the model is, with respect to the most updated information about the uncertainties of the unknowns in that particular model. Okay. So once we are able to do that, and then that's theoretically straightforward, is an expectation. Practically, it's computationally intensive. Once we do that, we optimize that function. So that integrated likelihood or loss, I'm sorry, this integrated loss. So it's computationally intensive everywhere, but any posterior model selection approach from a Bayesian point of view, or even non-Bayesian point of view, these days are very intense computationally, as you all know. So that's what we're going to do with this three-step procedure. So the DSS, that's this technology that we're talking about. It's a decision analysis based method, which is something comfortable. It's interesting because you separate the inferential aspect of learning from the decision making. The priors can be, you don't have to put too much pressure on the priors, because we know that Bayesian inference can be very sensitive to the priors you pick. You don't want to force in a particular direction if that is not the one that is going to be important for your decision making. Okay. And again, because when we talk about priors, we are thinking about the dimension of the parameters. When we talk about utilities, we might be talking about a much lower dimensional representation. For instance, I want to talk about the number of common factors in a factor analysis. So even though to get to that, you need to estimate, a very large number of factor loadings, idiosyncratic covariances, factor scores, and so on and so forth. You might be interested at the end of the day is, what is the best representation a factor model can give to my covariance matrix, and what is the minimum number of factors that I need? And then afterwards you can think about giving interpretation to the factors themselves, but you could separate those two things. So there has been like a few papers that extended that initial paper by Hen and Carvalho, this Pueltz and Carvalho, these ones were here. And then you can include here a fourth one, which is this one that I'm presenting, and including also this Call paper as well. So this is an area that is, it's just like a small wrinkle in the contribution to Bayesian statistics, but something that you might be interested in looking at. And just historically speaking, we do have a tradition of Bayesian statistics in Brazil. Bayesian statistics is like the black sheep of statistics for a long time, and Brazil is one of the countries with a chapter of Bayesian analysis, and there are Bayesians these days, like in most universities in Brazil, as in India and Turkey and other places as well, like even in China. So there's decoupling, shuriken, and selection, the DSS. From now on, I'm going to just say DSS. When DSS is applied to factor analysis, it will be more or less natural, even though painful to do computation and derivation, to what I just illustrated. So challenges that we encounter when we do factor analysis in high dimension, low or high dimension, is how to represent the factor loadings in a sparse way, and how to determine, or how to pick, or how to choose, or how to act, because we're talking about decision making, in terms of the number of factors. Okay. So there are several alternatives in the literature. You could do marginal likelihood, Bayesian model averaging, all very computationally expensive, infeasible if you go to extremely high dimensions, and also involve multiple steps. We have worked on sparse inducing priors for the factor loadings, including myself, have been doing that for a while as well. And sometimes you have to worry about overfitting priors because of the large number of factors. So you end up like restricting too much the model structure. So what we're going to do here is just say, well, if you think about a factor model, factor analysis, and if you think that you need 3, 4, 5 factors to explain, let's say 20, 30 attributes, characteristics, or features, these days in machine learning, they like to call those features. So if you have like 30 features, 50 features, 100 features, maybe 5 factors will be enough. What we do is we fit a 20 factor model. So we overfit the data, and then we, in the decision making step, we go backwards, and select, or at least to highlight how different fitting a 20 factor model is to a 10 factor model to a 5 factor model in terms of loadings and things like that. So that's the idea now, like very clearly stating of first fitting the model. That's what we call shrinkage, because when we do Bayesian statistics, we're always shrinking because we have a prior. If you just have the likelihood, you're not shrinking anything. But when you put a prior, you're always shrinking. There is always like a combination of the information that comes from the likelihood with the information that comes from the prior. When we do separate that from the selection, so the selection now is done afterwards. Once we do like the fitting, model fitting, combining prior and the likelihood for the factor model, we get a posterior distribution of this over-parameterized factor model, and then from that we go backwards. Okay. So the goal is to extend the DSS to the factor analysis model. And we show the degradation in utility in relation to factor dimension and the sparsity of the loadings. Those are the dual aspects of the factor analysis. Number of factors and how the factors affect the attributes. The loadings are the weights of the factors in a particular characteristic. So sparsity in the loadings means that some factors might be important, others might not be important to explain some of the traits. So we want to select the number of factors and determine the sparsity of the loadings simultaneously. And the method, as the DSS for linear regression, is agnostic with respect to the prior choice. Okay. So here's a standard slide from any class on multivariate statistics in factor models. So we have n observations, or let's say n individuals, can be people, countries, regions in a country, hospitals, and P are a collection of characteristics from that unit, I. So there are, like, as I said, n units. So P, if P is large enough, let's say 10, 20, 30, 50, 100, the idea is that it's very likely, and empirically we've been learning about that for over 100 years now, since the beginning of the 20th century with the Spearman's work on factor models, that this covariance matrix of a p-dimensional vector is most likely represented by a much lower dimension component, which down here at the bottom is represented by that B transpose. I'm sorry. So the idea of the factor model is this one that looks like a regression. You're basically saying, well, look, let's regress the y's on a vector of factors. Here, if you look at the f's, the factors, they are very similar to the y's. The difference is that the factors are, in principle, a priori independent, and the dimension of the factor vector is k, which is much smaller, potentially much smaller than n, and plus some residual noise that accounts for characteristics of the observations. They are not accounted for by the factors themselves. when we do that, and if we have a a probabilistic representation of the factors like this, what we are actually doing when we write a factor model like here in 1, what we are actually doing is saying the y's, the characteristics of the individuals, they are Gaussian, zero mean. That's not relevant right now. We can put any mean we want, could have other covariates and other kinds of structure for the mean, but assume that we already took that out. And a covariance matrix that has much lower number of parameters. So imagine that P here is 100. So we're going to have like 100 square divided by 2, but order.
Did we lose him? I think so.
I think he got disconnected.
Yeah, let's wait for him.
Yeah. Can anyone in the audience personally contact him? I mean, if they are in connection with the speaker.
Send an email anyway. And yeah.
Hello, Professor Carlo, do you know if
I'm not very close to him. I only have his email address. So the best thing I can do is, he's back. It's good when you call me because he comes.
Yeah. So he's back, I guess. Maybe he can reshare his screen.
So can you all hear me again?
Yes, we can hear you again.
Yeah. I don't know what happened. Just my computer just disappeared for like a second, and it turned it off, and so I just had to turn it on again. I apologize for that. I have no idea what it is. I will have to find out later.
Yeah, I hope it's nothing serious. Yeah. Anyway.
No, I don't think it is, but let me think about that later. So
Okay.
I know I broke the chain of thoughts here. So I'm glad at least we were talking about factor models, which is something that everyone, I guess, have studied at some point in his or her life. So factor model at the end of the day is a way to reduce the dimension of the covariance structure in a vector of data. So the key point, as I mentioned, is how to pick the k number of factors, and is that a way to make this B matrix as sparse as possible, meaning each one of those P characteristics might depend on as few as possible factors. So you can try to give names to the factors. This is pretty common in psychometrics and other areas where you ask someone to answer like 50 questions. Any one of us have done this in the past, and they look at those questions and try to see the certain latent traits as how expansive you are, how talkative, and how secure or how immature, and a few other characteristics of the individual based on these traits. Similarly, when you do like a national test, you do like a test with 50, 100 questions, and then they rank you according to how you performed in questions that were considered easy, medium, or hard, and that is driven by how other students also did in those tests, which is like this item response theory, which is also factor analysis. But at the end of the day, for us here, boils down to learning about B and learning about the F's, how many F's we need. Okay. The Bayesian literature, in fact, in lieu of time, the Bayesian literature on factor analysis is pretty vast. I'm not going to spend too much time explaining certain details. Posterior inference has been very popular using this lower triangular representation. But the point that we want to make is this one. For the factor model, this is the utility or the loss function we're going to use. It's all based on covariance matrices. The covariance matrix omega is the covariance matrix of the y's. So if you think about this bottom equation, B transpose plus sigma, that's my omega. The question is omega a function of k factors, k plus 1 factors, k minus 1 factors? How sparse is the me matrix, and things like that. So the question now goes to, once you have a representation omega, let's say, that comes from the posterior distribution, what is the best omega tilde that you can pick? So down here is what I'm talking about. So I'm going to choose that omega hat that minimizes the expectation of this utility function with respect to theta, where theta are the parameters that define the omega matrix, B transpose plus sigma. And then you say, okay, so that expectation comes from where? Well, comes from, you give me a bunch of data, I have a prior for B and sigma, I get a posterior for B and sigma condition on that bunch of data. Now, with that posterior, I construct omega, and that's it's the omega without the tilde, and I take the expectation with respect to that posterior distribution for a particular value of omega tilde. So I say, let me use this omega tilde that puts zeros in many places in the covariance matrix. Is that the one that minimizes the expectation of the loss? And that's the idea of, transferring to the loss function the optimization of which one of these omega is the best one. Okay. So that's what we do here. So we do transfer to the posterior distribution. And here's here's a simple derivation of how we get the expectation from the posterior. Is an expectation of that loss function plus the penalty that doesn't depend on omega. It depends only on the action omega tilde. And at the end of the day, this expectation only depends on omega, or the parameters B and sigma, through the posterior mean of that. So we just compute the posterior means of B matrix loadings, factor loading matrix, and sigma, the idiosyncratic matrix, and to reconstruct omega. So with that omega bar, that is a number that comes from the posterior, I plug that in here, and now I need to minimize this. So there is the whole thing that comes from the posterior distribution is in blue here. So now the question is, I'm going to fit a bunch of factor models, not fit, I'm going to look for a bunch of factor models that minimize this function here. In other words, that minimize this trace conditioning on minimizing these two other components. And that's the one that is close. So you see that you're trying to find some omega tilde which is as close as possible to omega bar, because to minimize this, you want to make this identity, right? You want to make this matrix the identity, so the trace is just P. But you also want to minimize that. So, and there is a penalty involved. So you don't want to, if you fit a factor model with more factors than necessary, you might be able to minimize this part here in the middle, but you might include, you might add some penalty, unnecessary penalty, to your maximization. So you can say, should I pick a 3-factor model or a 4-factor model? Both are very good fit, let's say this middle one. Well, then let's pick a 3-factor model, because a 4-factor model will induce more penalty, more complexity in my analysis, just like regular AICs and other schemes interact. So we do the usual Bayesian approximation via Monte Carlo methods. That's also something very common these days. And as I said, here, if I need to more or less finish with I'm going to give one example in 2 minutes, but if there is one slide that summarizes everything I've been trying to do here or trying to say, is this one. Because here I'm saying, look, you fit a factor model, like a saturated factor model with, let's say, 20 factors. Now I'm going to look for k tilde factors from 1 to 20. And for each one of those factors, I'm going to penalize more or less the loadings matrix. So there are 2 dimensions here. I'm going to scan through 20 factor models, and within each one of those, I'm going to penalize more or less. So there are many dimensions here as well, the loading matrix, and see which one will be able to capture this omega bar, which is the one that comes from the posterior distribution, as close as possible. So let me go and show you one. This I'm going to skip. That's just like the whole algorithm in one page. It's trying to show you that we do first posterior inference, we solve the maximization, and then now we compute these quantities to summarize our findings. And I think that's easier to see in a simple example. So I'm going to stop with this simple example. Here we have a model with how many? Let's see, 1, 2, 3, 4, 5, 6, 8 variables. P is equal to 8, and we have only 2 factors. So there are only 2 factors. And if you see this factor model, the first factor, which is the first row, is heavily loaded on the first 4 components and small for the rest. And the second factor loads more on the components 5 to 8. So in the second half of my vector. Okay, it's a simple example that we extracted from some old textbook. And we do an exercise with only 100 observations. So we only have 100 observations of a 10 variable 2-factor simulation. And what we do is, now let's see if we need more than 2 factors. Okay. So when we fit our scheme, this is the slide that summarizes everything. The number of factors that we are considering go from 1 to 5. So 5 is a highly saturated factor model for this exercise. We don't need more than 5 factors. And for each one of those columns, for the number of factors, we actually fit, we sparse, or not fit, but we search in the space of loadings matrix from very sparse to not very sparse. So like lambda here takes 10 different values, actually 11 different values. And what we do is we go from the right to the left, basically saying, do I get a good result with a 5-factor model, with a 4-factor model, with a 3-factor model? They're all similar, so I would stop here at 3. Well, how about if I go to a 2-factor model? Well, it looks very similar to a 3-factor model as long as you are within these boundaries. So then you can ask questions about the size of these boundaries. And that one in red is the one that we not only we go down to a 2-factor model, but we also ask ourselves, do I want a 2-factor model that has no sparsity or a 2-factor model that has some sparsity? So this red one is the one that has some sparsity. Okay, so the black one is no sparsity in a 2-factor model. The red one has some sparsity in the 2-factor model. That's where we stop. And you say, well, if you keep going, you're gonna go out of these boundaries, and then your other 2-factor models or 3, 4, 5-factor models are better to represent the covariance matrix. So this picture just summarizes, well, if I do have to give you, let's say the practitioner or the decision maker, a single response, I would say, well, just fit a 2-factor model and induce sparsity up to this level. And that's what we get here when we do. Here's the true loading matrix on the left. In the middle or on the right, we have the estimated or the chosen in a decision step factor loading matrix when we don't have any sparsity. So you see that this shade here is not completely white or here, but when we do induce some sparsity, we get the one in the middle. So the one in the middle is actually saying basically the first column is dark for the first 4 components, is more white for the second group, but this one here for the second factor, I can make it this more white, in other words, closer to 0, more than if I did not include any sparsity. So we pick 2 factors, we pick a 2-factor model, and we also induce sparsity. That is also part of the decision process. It's not part of the estimation process. That's the key ingredient that you come out of this talk. Okay. There is like a simulated exercise. I'm just going to go through. I think now I would have to stop, but you said that I have a few more minutes, right? Because I start late.
Yes,
It was my
fault. You can take it.
It was my fault anyway, but I'm going to take it. So just to show you, like in this exercise, we did like it's a very simple exercise, but it's based on real data. It's in psychology, they have this big 5 personality traits data. You can find in the R package psych and the function BFI, like a Bayesian factor influence. And the idea is that we have P equals to 25 personality traits that were collected from a much larger data set, but this one here for 126 observations. The N is 126. In this case, they are individuals age 50 or higher, like me, for instance. And so the data and everything is available online. Okay. So I'm just going to go to that picture. So we run with different priors. You know, top and bottom are different priors we used in the estimation step. But when we get to the decision step, regardless of the prior, we actually get to the same 3-factor model and virtually the same structure. So our scheme is like, in a way, robust regarding which prior from which group of authors you decide to use for your factor estimation. When you look and reconstruct the covariance matrix, you see, look, all of them are giving me pretty similar covariance matrix, but the one that we are, using, it's basically picking a 3-factor model to reconstruct these covariance matrices. Another thing is when we do look at the selection as well, like sparsity inducing, you see that we go from 24 factors all the way down to 3 again, and we can induce some sparsity. The red one here is basically saying, yes, you should induce, you should allow for some sparsity without deteriorating that much your model. Okay, and here are the 3, 4, 5 factor loadings matrices, for each one of those 2 representations when you do have and you don't have sparsity. Like on the top you have sparsity, on the bottom you don't have sparsity. Okay. So I think I'm going to stop here, basically saying there is one message that I wanted to convey in this brief presentation. One that is, for a long time we were too focused on making all the decision step of a more general Bayesian estimation procedure into the prior. But now this is, providing a way, and that's not something that we are the only ones doing that. I mean, lots of people have been rethinking or going back to the origins where you have the 3 ingredients. You have data, of course. You start as a frequentist or any statistician. You have a model, or several models. You induce past information through a prior, but you don't want to put too much information into that prior that you're not sure about. So you transfer that to the decision making, and then you make it clear what is the penalty that you're going to pay if you make the wrong decision. So you separate a little bit those 3 ingredients. And we did that in the factor model setup. The initial setup that was proposed was a regression setup because of the popularity of regression. But for those who work with multivariate statistics, I think a factor model would be the equivalent popular technique used everywhere from any area, from climatology to financial econometrics to EEG data, like neural data. And again, I want to thank you for taking your time to be here. It's an honor to represent Brazil and to see the audience from these 5 countries, and hopefully this will be recorded, so hopefully eventually some other people that were not able to be here today will listen. And if anyone has any questions, just email me. My email is my first name @gmail.com. That's a simple email, hedibert@gmail.com, and I'll be glad to try to answer, or at least to share references or points.
Okay.
Let me stop sharing here.
Thank you very much for your talk. It was very nice, and especially you gave it early in the morning. So let's thank Professor Lopes first. It's very early for him, so please join me thanking him. Okay, so is there any questions? So those who are in the audience in the hall, you can ask directly, or if you're in the chat, then if you're doing it online, then please write it in the chat. Or okay, so can I unmute you? Yeah, you can ask the question.
Hi, Hedibert.
Yes.
It's Paulo from Brazil. We actually know each other. So I have 2 questions. I'm from a completely different community. I'm an optimization guy. So I'm trying to translate things from your language to my language. So if I got something wrong, I'm sorry. But
no,
if
fine.
you understood well, controlling the factor is somehow related to controlling the rank of a matrix, right?
Yes, and this is exactly the same. The thing is,
because
with a factor
it's
model,
the BB transposed.
Yes, but
Okay.
remember that if it was completely BB transpose, then we are referring directly to the rank of the matrix. But we do have a idiosyncratic component that accounts for potential specific variability. So even though B might be reduced rank, and that's the idea, you want to be the BB transpose to be like rank K, because you have this diagonal matrix with non-zeros in the diagonal, the sum of the two, it will always be full rank.
I see. But my question is, because if I understood well, for you to control the factor, we're basically trying each possibility at a time, right?
Yes.
And looking for the end results. But in I don't know, in image processing, for example, when we want to control the rank of a matrix, we tend to use a penalty associated with it, which is the nuclear norm. So
Okay.
have you ever tried to use the nuclear norm to control this rank in an automatic way instead of looking at each possibility? Have you ever seen something that looked like that in your domain?
That's a good question. Not that one in particular, but when at some point in my talk, I had a loss function that had a combination of the likelihood of a reduced rank model. That's the one that you're talking about being automatic. But we also have a penalty that we basically use a norm 1 or norm 2 or some other type of norm for the matrix. But that one that you were mentioning, we never use. So I'm going to tell my co-authors to look into that. But yes, that's basically what we do. It's automatic. We don't do it like, it's always, everything we showed you is done automatically as well. But you raised a question that is a very important one. How we, how we design this loss function to be optimized. And so you can use many norms for picking the best loadings or the rank, but it will be a problem specific. So as you said, if you're talking about image, maybe that's the one you mentioned is the best one, that's more common. We should try that. In other areas, people are more interested in kind of other different types of norms. And what I'm saying is that is fine, because we are transferring, even if you and I fit the same model to the data, when it comes the time to decide about the structure of de facto model, the rank, we can vary depending on your utility or my utility or loss.
Any other question or comment?
Thanks, Paulo, for your question.
Are there any questions from the live or from the offline audience? Yeah, I don't think so.
Yeah, I don't see anything in the chat.
All right, chat. So just a thank you here from Paulo. Thank you, Paulo. Thank you, everyone. And I hope you guys have a wonderful, well, what time is it there now? Like
in India, it's evening. It's like almost like 8 p.m., 7:55.
Okay, dinner time.
Yes, yes. Yeah. So thank you very much for your talk. Very nice talk, and also thanks for accommodating us. It's like very early there, as you said.
No,
if it
it's
was
fine,
in Brazil, I think it would be around 11 o'clock now, right?
Yeah.
11.
Now is I'm gonna go and
Yeah.
organize my kids to go to school.
Okay. Okay. Okay then. Yeah. Okay. Thank you very much for everyone. Let's thank him once more.
Thank you all. Good luck with the conference, the rest of the conference.
This marks the end of day 2 of the conference. We will also meet again for day 3 of the conference tomorrow morning in India. Thanks everyone for joining, and this would conclude the session for today.